Shivram, at 6:42, we can start the videos.
Majority of students end up in many colleges across the country, and quality varies a lot from college to college. What should a premier educational institute like IIT Madras be doing? And NPTEL is an answer to that.
NPTEL is an online courses or a MOOCs platform. We can call it a revolution in online education.
Today, nptel.ac.in, our website, is one of the largest repositories of engineering content in the world.
Type of students that we are able to reach is a fairly broad spectrum which goes into this idea of lifelong learning.
NPTEL with the local chapters is actually a very collaborative environment in which we want to cooperate and work with the colleges rather than being a competition.
Wherever you are, whoever you are, if you're interested, you can learn.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
Although electric vehicles or EVs are all the rage today, India still imports most of the batteries required to run any EV. This is finally changing. Indian government has recently laid down encouraging policies to move from petrol and diesel based vehicles to electric vehicles, and research at CB will have a direct positive impact on this shift, making India and this world a greener place.
With IIT emerging as one of the top engineering institutions and educational institutions, the hospital staff take pride in telling you that we maintain the health of all the staff and students. The Institute Hospital has about 11 doctors, 14 staff nurses, 8 nursing helpers, and a host of administrative staff, and we have outsourced our departments, the pharmacy, the lab, as well as the ambulance and housekeeping services. With an aim to maintaining quality of our care, we have accredited ourselves with the ISO 9001-2015. We maintain the holistic health of all the staff, the students and the project staff who come to us, making sure that they get good evidence-based medicine.
a very good world-class gym facility with standards for everything, like for cardio, high-intensity training, weight training, Tabata workout, everything here.
The sporting culture here is one of the best in the city, and we have great facilities.
What I find is the facilities here which we have got is really good.
And the facility that we have to practice our own table tennis game.
The coaches are really friendly, they are really experienced, and
It's a place where you can play without any selfishness.
Thank you, Shivram. Again, that was a lovely collection, by the way. So, a very good evening to everyone who present virtually through Zoom and YouTube. So, this is Rudra from the Office of Global Engagement, IIT Madras. These IRIS webinars are the idea of IIT Madras to showcase the innovative research that is being generated at IIT Madras to various stakeholders like researchers, industrialists, and policymakers. And I'm very glad to share with everyone that this IRIS webinar series is gaining a momentum in the public domain, and we are receiving more number of participations from the public. And it's my pleasure to welcome you all for this 37th webinar of this IRIS webinar series. So today's webinar is on energy storage conversion under the cluster energy, propulsion and renewables. So this research initiative project is being led by Professor Godandaraman. So to introduce Professor Godandaraman Ramanujan, Professor Godandaraman did his MSc in the Anna University and completed his PhD on solid state chemistry unit at Indian Institute of Science, Bangalore. He is a fellow of the Royal Society of Chemistry and fellow of the Academy of Sciences, Chennai. He also, as the guest editor for upcoming focus issue, Energy Storage in China, in the Journal of the Electrochemical Society, and also serves as the Vice President of the Indian Society of Electroanalytical Chemistry for the period of 2021 to 2024. He has won 12 sponsored projects and 4 consultancy projects so far, and notable among them are like 4 crores consultancy grant from the ONGC for developing flow batteries at TRL5. He also published 100 research articles in international peer-reviewed journals, and 2 book chapters, obtained 1 US patent and 1 Indian patent, and applied for 5 Indian patents. So joining as one of the speakers of today's program, we also have Professor Venkata Krishnan. Professor Venkata Krishnan is an associate professor in the Department of Chemistry, IIT Madras. He did his PhD in the Department of Chemistry at IIT Kanpur. He also, his research interests are synthesis of novel function organic molecules for lighting, field effect transistors and photovoltaics, energy efficient organic dyes for bioimaging, nanoscale self-assembled architecture for functional devices. He also has 37 peer-reviewed publications and a total citations of 1068. So with 2 professors joined as the speakers of today's program, we also have Subramaniam Surya Narayanan. Professor Subramaniam has joined as the moderator of today's program. Professor Subramaniam is currently working in the Department of Chemistry and Biomedical Sciences at Linnaeus University, Sweden. He received his PhD from IISc Bangalore in the year 2007, and back in 2006 he received a research fellowship from Orcus India program for the project Functionalized Surface of Nanobiosciences, and in 2008 he received Marie Curie Research Fellowship for the project entitled Nanomaterials for Application in Sensor Catalysis and Emerging Technologies. So it's my pleasure and honor to invite you professors to this session. Note to the audience, please ask your question in the Q&A box. Please like or upvote the question that interests you so that the moderator can prioritize them. Over to you, Professor Subramanian. Professor, I think you're mute and you have to unmute yourself.
Hi. Now, I guess the schedule is around 6:45, right? Yeah.
Yes, Professor. Yeah.
Who wants to start first? Yeah, is it Raman or Venkata Krishnan?
Subbu, I think I will be going first.
Okay. You want to share the screen?
So, Rudra, can I share the screen? Would you permit me?
Sure. Yes, Professor.
Yeah. Is it visible?
Yeah.
Yes, sir.
Okay, so I should go on this. Yeah, I think it's full screen now.
Yes, Professor.
Yeah. Okay. I welcome you all for the 37th webinar, IRIS webinar series from IIT Madras. And for all of you, very good evening. And this seminar is basically to introduce our center, that is an advanced center for energy storage and conversion. Okay, so this center, and before beginning my talk, I thank Professor Venkat. This is our new entrance. So it's only a few days old. So excellent new entrance, very wide and 3 lanes and so on. So it's a new entrance. Probably you will not find this picture now in the internet. Probably to take few days. So, and this is a famous Gajendra circle. So this inside the IIT Madras. Somewhere close this Gajendra circle is our chemistry department is located maybe 100 meters away from here. And one is myself. I am an experimental electrochemist working on various, excuse me. Yeah. So I'm an experimental electrochemist working on various application-oriented research, electrochemical research like batteries, solar cells, and fuel cells, and so on. And Professor Venkata Krishnan Parthasarathi, he is an expert in molecular switches, sensors. I mean, Rudra, am I audible?
Yes, Professor, you're audible, sir.
I think in between there was...
we cannot see your video though.
Okay, so I think the video automatically got off. Let me check it. Why is it so? So when I went for this laser pointer, something happened. Just 1 second. Is it now back?
Yes.
Yeah.
Yes, Professor.
Okay. So, Venkata Krishnan is an expert in the molecular switches, sensors, and organic luminescent molecules, dyes, and basically is a synthetic chemist and also a photochemist. And we have our mentor, Professor Indrapal Singh. He is known for his work on carbohydrate chemistry, synthetic carbohydrate chemistry. He prepared several biologically and medicinally important compounds. And when myself and Professor Venkat joined IIT Madras, so we kind of dragged him into electrochemical research because we value him for his rich experience in organic chemistry. So we collaborated with him, a lot of redox active molecules for batteries, for solar. These are made with. And last one is Professor Ramaprabhu. He is an storage of late lithium sulfur batteries and solar cells and carbon dioxide capture and conversions and so on. Besides these 4 core members, okay, we have collaborators from in and out of IIT Madras. Dr. Arvind Kumar Chandran, he is associate professor from Department of Chemical Engineering. So he's an expert on solar cells, solar water splitting, and carbon dioxide reduction, photoconductivity, and so on. And we have 2 scientists from industry called Inventors Bioenergy Private Limited, Dr. Harini Priya. She is also our alumni, and Dr. Sudha Venkatachalam. So their contribution is mainly going to be on system level modeling for this work. And this center has 2 verticals. One is lithium sulfur battery. The other one is organic photovoltaics. So lithium sulfur battery work is mostly done by myself and Professor Indrapal Singh and Professor Ramaprabhu. And the organic photovoltaic works mostly headed by Professor Venkata Krishnan, and myself and Professor Indrapal are partner to it. So why we look for lithium sulfur battery, although there are many lithium ion batteries around now? Because the commercial lithium ion batteries, you can find even up to 350 watt-hour per kg if nickel-rich cathodes are used. But the common ones are like 150 to 200 milliampere hour, that translate to about 300 watt-hour per kg. But this technology already reached its ceiling in terms of capacity, because this technology is based on the intercalation chemistry. There are only so many crystallographic active sites are available in a host structure. Therefore, the amount of lithium that we can insert and reinsert are limited. In sometimes, like in cases of lithium cobalt oxide, for example, you can't extract all the lithium out of it. Only a part of it can be extracted in order to maintain the crystal structure stable. So therefore, the research now is focusing on shifting to a conversion-based chemistry instead of a insertion-reinsertion-based chemistry. So in that, lithium sulfur has a lot of promising. It's a very promising conversion chemistry, and moreover, lithium is very abundant. So considering its high capacity of sulfur and high energy density it offers, together with the natural abundance, we kind of chosen this lithium sulfur work. Probably we can extend this for sodium sulfur and other conversion-based chemistries as well. So I just introduced the problem in this sector. Sulfur is used as a cathode material here, but the sulfur, before it will go through a series of polysulfates. Ultimately, it will become lithium sulfide. But those polysulfates, which I have shown here in green, are highly soluble in the electrolyte that is used in this lithium sulfur battery. So what's the problem? These electrolytes, which are soluble, kind of migrate through this from the cathode to the anode, and it poisons the anode, or it passivates the anode, thereby making the cell to lose capacity cycle by cycle. Moreover, these polysulfates are displaced now from the cathode to other parts of the cell. And the one which I have shown in blue, insoluble. Therefore, in sulfur, through a solid form of sulfur, La2S8, La2S6, and so on, and then again becoming insoluble. Therefore, if you see this discharge curve that I have shown here, it has got a two plateau. The first one is because of the sulfur A2 polysulfate, those green polysulfate that I have shown here. Okay, the second one is because of the soluble sulfides, polysulfides to insoluble lithium sulfide. Okay. So, but we have used biomolecules as binders to confine these polysulfates within the cathode structure. So we have done such modifications, and we are able to reach up to 1 milliampere hour per gram of capacity even after 100 RC rate. Other approaches that we have is not letting this sulfur go into solution. Correctly, insoluble form of sulfur, La2S2 or La2S. Okay, so for that we have used some confinement chemistry. Therefore, you don't see a two plateaus here. There's only a single plateau here. Moreover, this polarization, that is the voltage difference between the charge and discharge curves, also very minimal here. Okay, so the energy loss because of storing and retrieving of these charges are very minimal in this case. And the other approach that we follow is use of ceramic separators. If in case this lithium polysulfates moves towards anode, the ceramic separators that is placed between the anode and cathode is kind of absorb these polysulfates, thereby protecting your anode from the capacity loss. So like that, there are many approaches that we follow as part of this lithium sulfur program in this center. So these are the facilities which is as of now exist in our center for the battery chemistry, like glow box. There are several of them now, and cyclers for charge discharge testing, or for any other electrochemical testing like cyclic voltammetry, impedance spectroscopy, and so on. And there are other accessories like electrode making, punching machines, and so on. As part of this PCOE, we are augmenting the facility. Shortly, we will have a complete 2 ampere hour pouch cell making facility besides this that I have shown here. And in fact, we are looking for scientists from outside IITM as well. You are welcome. If you have an interesting idea to collaborate, you are welcome to collaborate with us and utilize all these facilities at IIT Madras. And coming to the organic photovoltaics, one of the system that my group works on is the dye-sensitized solar cells. Dye-sensitized solar cells traditionally has utilizing two types of dyes. One is metal-based dye, like zinc porphyrin that I have shown here. Other one is metal-free dyes, the one that I have shown here. These are some of the best reported dyes in the literature that you can find. If you look at this architecture of these dyes, generally it has got a donor made of any of these moieties like zinc porphyrin or triphenylamine, carbazole, triazotrexine or indolin. And then there is a spacer, this is a pi spacer, and an acceptor, which basically anchors with the semiconductor surface like KO2 surface. Okay. So when you shine the light, the electron will be flowing from the donor to the acceptor through this bridge into the conduction band of the titanium dioxide. So these are some of the molecules which has been synthesized over the years in our laboratory in collaboration with Professor Indrapal Singh. So we have gone up to about 9% efficiency with the architecture developed in our own lab. And we also developed techniques like electrosorption dyeing, wherein we can prepare the photoanode in less than an hour. And we can make the entire device in less than 2 hours or so. Otherwise, the conventional dyeing requires about 12 hours or so. So we have made some advancements in terms of device making as well as in terms of new engineering, new dye structures for organic solar cells. But our ultimate aim is to go for the solid state dye sensitized solar cell, wherein we don't have a electrolyte like iodine iodide, liquid iodine electrolyte. Instead, we'll have a solid state electrolyte. Therefore, the durability of these devices is going to be much better than the liquid based one. This is recent NREL chart that is released on the efficiencies of the different kinds of solar cells. The one in the purple are generally used in the space application. They are very expensive to make. And the one in the blue are commercially available, but they're expensive. And also you need a specialized fabrication facilities, like because it involves semiconductor technology, which as of now, we don't have in India facilities to make such systems in bulk. And the one in red are the organic type solar cells. So the one I'm talking about is dye-sensitized and perovskite solar cells here. So a reported efficiency of about 14%, a certified efficiency of about 14% is achieved with these kind of solar cells. The next chart shows the modules, the best module efficiency that are achieved using this organic solar cell technology. As you can see, the organic solar cells has got, is utilized, has come up with 200 to 800 centimeter square area. It's a very large area as far as organic solar cell concerned. So there are scope in in working on these molecules to improvise, because basically these solar cells, the perovskite or DSSC, are much cheaper compared to the other technologies which are based on semiconductor and monosilicon and so on. So this slide explains basically the operations or the mechanism that is involved in dye-sensitized solar cell. This central part here, that HOMO and LUMO. So this the HOMO means highest occupied molecular orbital, and LUMO means the lowest unoccupied molecular orbital, which is basically a virtual orbital, doesn't have any electron in it. So when the light is shined on the dye, you would see an electron promoted from HOMO to LUMO. It's basically an excitation. Okay. So if you have an excellent device, a dye-sensitized solar cell, then the voltage that you should get should be proportional to the energy gap between the HOMO and LUMO. But unfortunately, we don't harvest this entire energy of photon in this process, because the conduction band of your semiconductor is at a level lower than the LUMO of your die. Therefore, this much of energy, heat energy, it's a kind of over potential for us. Okay. That's not, the slide is not moving. Yeah. And the other point you could see here, the hole moves from the HOMO of your oxidized dye into the electrolyte. Generally, electrolytes are like iodine triiodide type of electrolyte which are used here. Again, there is an energy level mismatch between these two. Therefore, there is a voltage loss at this point. So there is a voltage loss while injecting the electron into the conduction band, and there is a voltage loss because of regeneration of this oxidized dye by the electrolyte and so on. And besides, we have other processes like back electron transfer. So the electron which is injected in the conduction band may end up in the HOMO of your oxidized dye, or may end up in the electrolyte. So, or you may have a luminescence instead of injecting the electron, you may have a luminescence from the dye layer and so on. These are the back electron reactions by which you will lose the voltage in the cell. So these are unwanted back reactions. So our group is interested in reducing the energy gap between the LUMO and the conduction band, interested in generating the electrolyte such that it is very closely spaced to the HOMO of your dye. Therefore, we can harvest the maximum voltage that is possible from these devices. So as I said in the previous slide, the voltage loss basically the difference between the band gap or the energy gap between the HOMO and LUMO and the open circuit voltage that we observe experimentally. So this is contributed, this loss is contributed by three different processes. One is the voltage loss at the injection stage, at the regeneration stage, and because of the back electron process. So this voltage loss severely limits the power conversion efficiency of these dye-sensitive solar cells. So therefore, the efforts are on developing high voltage electrolytes. For example, in 1991, iodine triiodide was used. It's about 0.4 volt with respect to NHE, but the latest is use of CuDMP. So this has about 0.94 volt. That means literally about 0.54 volt you can gain using this electrolyte instead of conventional iodine triiodide. But as I said before, our ultimate aim is to generate a solid state electrolyte. Therefore, we will avoid this liquid in between the anode and cathode here, and then we'll make a complete solid state dye-sensitized solar cells. And at this point, I request Professor Venkata Krishnan to share from his part and continue this presentation. And thank you for listening.
Okay. Good evening. Good evening to everybody. Am I audible?
Yeah.
Yeah. Thank you. So thank you, Raman, for the great introduction about the center as well as the battery related work and the DSSC work that we are planning to do in our center. So it's nicely connected, I feel, because DSSC was the origin for the development of perovskite solar cells. And for the past decade or so, the perovskite solar cell technology has taken off, and it's the most talked about solar cell area, I would say. Okay. The reason is because you see a rapid growth starting from the light to power conversion efficiencies from 3.8 to all the way up to 25.2% in just 12 years time span. Okay. So this has motivated the scientists all over the world, hoping that the commercialization would anytime be soon possible. Okay. So that's about the perovskite solar cells growth. But when you look at the cost and the lifetime, when you always look at the golden triangle, you always compare its efficiencies versus cost and the lifetime. The cost of making perovskite solar cells is less than half of the price of the silicon, crystalline silicon. Okay, so the efficiency wise, well, they are quite close. Now we may have to go from 25.2 to boost it to beyond crystalline silicon solar cells efficiency. But with the cost has to be cut down enormously. So all over the world, efforts are in progress to cut down the cost as minimum as possible. And when you talk about the lifetime, this is the main bottleneck, I would say, because the stability of the perovskite solar cells is a concern, and hence lifetime is very much limited to 1 year under Argon atmosphere. Okay, so if you have a nice encapsulation, probably you can extend it to close to 1 year or so. So this is the bottleneck. So more amount of research efforts must be put into developing stable perovskite solar cells, which can then in principle become commercially viable. Okay, so having, I mean, we are talking about perovskite solar cells. The main component in perovskite solar cells is the organic, inorganic hybrid perovskites, which actually has a formula of ABX3. Okay, so that is the chemical formula. A is the monovalent cations. It could be methylammonium or formamidinium cation or a simple cesium cation. And when you talk about B, that is the divalent cations here. Usually it is lead 2 plus or tin 2 plus. And X is the monovalent anion. It could be chloride, bromide, or iodide in this case. And an ideal scenario of a perovskite, okay, so this has a cubic symmetry. Its backbone comprises the corners of BX6 octahedron, and the A is located in the cube octahedral spaces. Okay, so structurally it looks quite simple. You can think of various combinations of the cation and the anion. You can mix them up. You can in principle generate gamete of structures comprising perovskites. Okay, so that is the beauty with this perovskite structure, and it's also unique in terms of physical and chemical properties. They have ambipolar charge transport. It has huge intense light absorption, which means the molar extinction coefficient or the absorptivity coefficient is quite high for this kind of materials. And as I said, you can also tune its composition. Cations and the anions can be fine-tuned, and thereby you can also vary the absorption, and thereby you can also tune the band gaps. They have small exciton binding energies, which means you'll be able to split the holes and electrons quite faster. And they have a long carrier diffusion length also, and they have high charge carrier mobility, and the solution-wise process is what often done for the fabrication of perovskite solar cells, which actually involves a simple technique and also a low-cost method. Okay, if you look at the device configuration of the perovskite solar cells, you see the perovskite is sandwiched between the transporting layers, hole and electron transporting layers. This is the main absorbing layer. Upon light illumination, the perovskite layer absorbs the light, creates holes and electrons. Electrons are extracted by the electron transported layer and then reaches the transparent cathode. If the holes are extracted or transferred to the hole transporting layer and then extracted by the metallic cathode. Okay, because of the ambipolar nature of the perovskite, you will be able to use the perovskite in any of these device configurations. That shouldn't be a problem. Either the NIP device or the PIN device. Mesoporous structure device were used earlier. Now the planar configuration is what is commonly preferred. And what you have is the swapping of these layers in these two device configurations. Okay, what you see here is the whole transporting layer next to the metal contact, but on the other case, you have the electron transporting layer adjacent to the metal contact. What is more important to us in this center is to focus mainly on the hole transporting material. The job of the hole transporting material is to extract the holes and then pass it on to the electrode actually. So there are a lot of interest in developing novel hole transporting materials because this seems to be the layer that is sitting on top of the perovskite, particularly in the NIP device configuration, where this prevents the moisture entering into the perovskite and provides some kind of a stability to the perovskite decomposition. Various hole transporting materials are reported in the literature, and the key ones are the three-dimensional ones that is shown in the yellow color here. And you also have the two-dimensional planar highly conjugated materials being used as whole transporting materials. I want to bring your attention to this particular structure, which is pyro-OMe-TAD, where the structure encompasses the two pi planes that are orthogonal to each other. When they are orthogonal in geometry, then the pi stacking between the neighboring molecules is somehow prevented, and the peripheral R denotes here the diaryl amino groups. So the peripheral diaryl amino groups would keep the molecules far away and hence thwart crystallization actually. And that's because that's one of the reasons why such kind of molecules are close to amorphous, or they are beautifully amorphous in character. As you can see from these slide, these three-dimensional molecules, which are spiro in configuration, have power conversion efficiencies beyond 15% values. Okay, but on the other hand, if you look at the planar structures, well, they are planar, highly conjugated, so one can, in principle, bring in the pi stacking, and hence the charge transporting pathways can be enhanced. But on the other hand, morphologically, they don't give a very uniform, smooth films actually. So that is the problem with this pi conjugated structures, whereas these structures have low hole mobility because they don't allow pi stacking. But on the other hand, they have beautiful amorphous character. How do you blend them together, right? So that was the question we were asking. And in our laboratories, we have recently demonstrated that synthesis of bicarbozoles are indeed possible, starting from simple carbozoles if you employ a simple organic oxidants. By this way, you will be able to eliminate any metal contaminants, which are often reported to be contaminated with the whole transporting materials in the final step usually. Okay, so by replacing the metal contaminants by simple and organic oxidant, you will be able to create bicarbazole whole transporting materials. So we looked at in detail about these compounds. They have a twisted geometry because the ortho-hydrogen repulsion in the solid state would keep them slightly twisted, but not to an extent of the spiro-OMe-TAD that we talked about. We just thought, how can we capitalize this twisting and fabricate perovskite solar cells and evaluate the performance of these whole transporting materials. Keeping that aspect in mind, we synthesized simple whole transporting materials. You can make them readily in gram scale in the laboratories. When you put them into the perovskite solar cell device configuration, when you use this compounds here, as is shown here in orange, red, and green, these three molecules have very convenient homo energy levels for the holes to be injected into them. Okay, look at the LUMOS, they are quite high, and thereby recombination of the electrons with the holes is hindered. Okay, so these materials are very suitable as a whole transporting material to be used into perovskite solar cells. When we use them alone, they have power conversion efficiencies about 13%, 13.3%. But when you use this as a passivating layer between the nickel oxide whole transporting material and the perovskite absorbing layer, and so the power conversion efficiency of these devices shooted up to about 19.49%, okay, close to 20% power conversion efficiency. Basically, these whole transporting materials are acting as a device defect passivation agent in the perovskite solar cells because these are coated on top of this. So you have the defect passivation layer. It also gives some kind of a hydrophobicity to the layer, and hence the moisture ingress into the perovskite layer. Besides this, it also provides a larger grain size, and hence you have uniformity and extended absorption and the excellent charge transport characteristics within the device. Okay, so if you look at the stabilities, we've also done the stability studies for these compounds. When this was put into the perovskite solar cells under argon atmosphere, only 4.55% decayed after 168 hours, but retaining 90.8% of its power conversion efficiency after 1000 hours. So this gave us some hope that indeed we could synthesize nice whole transporting materials based on the strategy that was explained earlier, fulfilling all the ideal characteristics of a whole transporting material. So we thought of modulating the core and also the periphery. So one can even expand the core, can also think of shrinking the core, and but retaining the peripheral substituents more or less the same, or you can also tweak the diaryl amino units. and vary its characteristics and look at in detail about their performance in perovskite solar cells. By doing so, what you are basically doing is by expanding the core, you are also bringing in larger pi conjugated systems, but by shrinking them, you are minimizing the pi conjugation, but retaining the spiro. So spiro is good for morphology, but the pi conjugated system is good for transportation. So if you are able to do that, well, we are looking at the efficient devices at the end. So with improved hole mobility, hydrophobicity, and an improved film morphology, can we construct stable perovskite solar cell devices? Is a question that we asked under this center. So we are trying to explore these kind of things using a simple metal-free, metal contaminant-free approaches. Yeah, so this is a facility we have with respect to the synthesis. We are basically organic chemists, and we have various experimental tools to characterize them. Okay. The other picture shows the cell fabrication facility that we have at IIT Madras. And this is the dye-sensitized solar cell facility developed by Professor Kodandaraman. And as you see here, you have the screen printer for the TiO2. And you also have the silver line contacts that can be done in a robotic fashion. You also have the UV curable paste machine at the end just to protect the silver line contacts. This is the fabricated device, DSSC device, a larger cell device that I would say, constructed in Professor Kodandaraman's lab. Solar simulator, we also have the annealing setup, die coating setup, and the high performance computing center. Just before you do the synthesis, you'll be able to get enough data about the molecular performance and the molecular characteristics. We also are planning to procure the PCE with integrating sphere. Soon it will be installed, I hope. And with this, I thank you so much. I'll be happy to answer any questions. Thank you so much.
Thank you, guys. Now it's my moderator job. I have few questions, but I don't want to bore you guys. I will have some questions, and if the other people they want to join, they also can share their views. And most comments and suggestions are welcome. I'm basically a chemist who is looking for conversion process and storage devices also. But as Raman mentioned, that the lithium battery has reached its ceiling. So I couldn't find Raman. Is he there still? Okay. So there are so many things going on with the lithium and battery. So what do you think? There's this more sophisticated and speciality that it brings in when you add the sulfide and lithium sulfide batteries. What may be the innovation or rejuvenating thing when you introduce lithium sulfide battery?
Subbu, can you please repeat, because I had a temporarily I was out from this meeting room. Yeah.
As you mentioned, it is known that lithium-ion batteries are everywhere. It has reached its saturation level. So when you introduce lithium sulfide, so what is the new thing you expect, and what is the new thing do you think you can bring it in the current trend?
First of all, this the sulfur capacity is higher because it's based on conversion chemistry. Okay, so for example, if we are using intercalation based graphite as anode, you get about 372 milliampere hour per gram. And if you take lithium cobalt oxide, say about 120 to 30 milliampere hour per gram, right? So even the nickel rich materials, as I said, you can go maximum up to 200 milliampere hour per gram. So, but if you use sulfur chemistry, at least you can enhance this capacity by at least 10 times. Okay, So if you are going to use this battery for automobile application, upon successfully developing or perfecting the technology related to lithium sulfur, you may able to have a long distance flying vehicles for charge, which at the moment is a bottleneck for lithium ion based batteries. Yeah.
Okay. There was one of the, in one of your slide, you mentioned, I think slide number 2, I forgot it. This in the lithium sulfide, this thing that you mentioned about some biomolecule.
Yeah. Yeah.
What is that? Because of course something is going on in the biomolecule, I know, but what's your plan? What do you want to? What do you think you can make with the biomolecule?
Basically, we are using it as a binder as well as something that establishes a chemical interaction with these polysulfides. Okay. Therefore, they don't cross your cathode. The moment you let it dissolve in the electrolyte, the issue is it can go all the way to your anode, lithium anode, so it can passivate the surface. Then you will lose some of the lithium, and that may also increase the resistance of your cell. That may turn into a non-usable cell. So by doing this confinement, basically by chemical interactions, yeah, by doing this confinement, we'll be able to reuse this sulfur over and over again. So we can extend the number of cycles to many thousand cycles. So as of now, it is, even within few hundred cycles, we have this capacity of this lithium sulfate batteries fading away, but that can be delayed by these kind of molecules. At the same time, these molecules has to be stable in the environment that we are looking at. Yeah.
Biomolecules is another option because it can bring in some environment friendly attitude also. That's why
environment friendly.
And
some of them may be solution processable. That's also one of the criteria when you are making the electrodes. Yeah, it's be easy to process.
Yeah. Of course, biomolecule is not that easy to handle, but if it is the best option, then if it brings in, then it will be good. I have a few questions, especially on the dye-sensitized solar cells. That was quite interesting. And you introduced the ferrokit. I know that a group in Norway, they are very much working in ferrokit-based solar cells. I'm not in touch with them currently, but earlier I was in. This ferrokit, do you think that it's not commercially available right now? How fast is it going to be commercial? How fast we can bring it in commercially?
Raman, you want me to answer? Shall I go ahead?
Yeah. Yeah, please go ahead.
Yeah. Right now, the bottleneck is the stability, as I mentioned. So efforts are in progress to make it a stable device first at a laboratory scale, and then they would commercialize it. So before that, a lot of research interest must be happening at the degradation, understanding the degradation mechanisms and so on and so forth. So roughly from now, I would say about 10 to 20 years down the line, probably. It can be commercialized on a larger scale, I think.
This ferrokit structure, it's not very easy to optimize, but still it gives a good output. But I have you showed this. There's the one of the component in ferrokit is the lead.
Yes.
It's not environment friendly, right? Do you have any other option?
People have also tried with the tin. People have tried with tin. So, but the efficiencies are not as good as lead-based perovskites. So that is another limitation. When you switch to other cations, then the performance is not so great. I mean, they are not able to match the performance of the ones that are obtained with lead-based ones.
When you bring in new things, we have to, like ferroskids says, you have to always mention what is the speciality of the existing state of the art. how good it may be in overwhelming or overriding the state-of-the-art current trend in solar cell. What is the speciality that you can bring in with the perovskite?
The very important point is that it right now is very close to that of the efficiencies of crystalline silicon. That's one satisfying aspect with the perovskite. So a little bit more research on the stability as well as the cost for a large scale. If that could be optimized, then it will become a reality, I feel. So the potential is there. Yeah.
Yeah. Okay, but I have noted a few more questions. But yeah, one more thing. I always have this doubt in dye-sensitive solar cells. Titanium is the only element which is much better in efficiency. Of course, they make certain nanoparticles, and then it's this one. Is there any other form of titanium instead of nanoparticles? Maybe any other nanostructures of titanium has been ever explored in terms of efficiency? Like you said,
there are.
Yeah.
There are several nanostructures, even because the rutile and anatase forms of TiO2 and their mixture, for example, they have been tried, and nanorods, hollow rods, right? All these kind of things are tried. In fact, in our architecture itself, we use two types of layers. I mean, everybody uses that way. Like we have a transparent TiO2 layer with a very fine particle, and then we have a 20 micron thick particles, which is forming the scattering layer, which basically doesn't absorb the dye, but it helps the multiple scattering of light inside the solar cell, so that increasing the probability of light capture by these dyes. Right? So all kind of nano forms have been explored so far. But why titanium very specific, very good electron mobility and so on are the reason why, and the wide band gap, and also the most of the dyes that we develop, so whose LUMO just above this the conduction band of your TiO2, all that matters. Otherwise, there are so many semiconductors. You can go for it, like zinc oxide, right? Zinc oxide also is explored. So there are so many other metal oxides also available, semiconductors, yeah. But not all of them can be used. There are some basic criteria that it need to fulfill, like it should be transparent, and it should absorb these dye molecules. Generally, we use this cyanoacid acid as a linker for all these dyes. Mostly, this is the best known linker so far, although there are several of them available, right? So, yeah, answer to your question, yes, several nanostructures have been explored in the past.
Yeah, I have a last question. The cost of the solar cell, as for instance, what you said, the perovskite solar cell, is much cheaper than the silicon-based cell, right?
Yeah.
How feasible it is in bringing in the state-of-the-art technique or current trend? Do you think it's going to be much cheaper than the silicon this thing, or it is still they have to go a long run or long way?
It can be. It is definitely cheaper than the silicon. So we are, as I said in the beginning slide, we are less than half a price of the silicon. We are also close to the power conversion efficiencies. So of the silicon. So having high power conversion efficiencies, but on the other hand, you also have the cost lower, is kind of beneficial. This gives a positive feel that you will be able to definitely expand this to a large scale devices. But it as you said, is going to take a long time. Yeah, it's not going to be any time sooner. I believe already there are dozens of companies working on it, both in Europe and China as well. So they are going to be the front runners, I believe.
Yeah, as I mentioned, there is a group. They are working in Norway. They are looking at the perovskite structures and the solar cells. It's definitely a good one. It may right candidate for alternate for the the dyes means sensor, which is a solid state capsule. I guess I'm fine. I'm convinced with your answers. I wish you guys good luck. I will.
Subbu,
I couldn't hear my fully.
Venkat and Subbu, I see some questions in the Q&A.
I have. I come to that.
Okay.
Yeah, I'll come to that. But I feel that you guys have done a good job, and hopefully we can be satisfied. But there are some questions out there. I don't think I can. I'm going to ask all the questions. There is a question. This was writing that there is what is the these conversion reactions? What you mentioned in the Dyson solar cell. Sorry, not in the batteries. Will it affect the reversibility of a battery? The question is whether these conversion reactions in the electrodes affect the reversibility of the battery.
Yeah, this conversion reaction, if it happens as we envision, like Si to La to S, without undergoing any dissolution, and again back from La to S to S8 without undergoing any dissolution, then of course your battery will be highly reversible. In the sense, the capacity wouldn't change with the cycles. Okay, but in reality, it is not so. So, because the sulfur dissolves in the form of polysulfates, higher order polysulfates mainly, and they get displaced from your cathode to other points in your cell, for example, into your what do you call that, separators, or into onto the anodes that are present, right? So once it goes on to the separators and gets absorbed there, then it's not available for electrochemical reactions from the next cycle onwards, right? So therefore, you would see a drop in capacity with cycles. Whereas, as I showed, one of the strategies that we adopt fast is like doesn't allow this dissolution to happen first. We will convert S site to La to S directly, or even if you go through polysulfates, we will not let it go out of the electrode. Yeah. So all these strategies are done mainly to impart or mainly to improve the reversibility of the cathode. Right. So it is possible. It is work under progress. Yeah, we do have some success. We have gone up to 1500 milliampere hour per gram at 0.1C with some of the modifications that I have indicated to you. Yeah, but we would like to see, because these are all at coin cells. We would like to, as I said, as part of this PCOE, we would be having this pouch cell making facility, so
yeah,
that can be tested in the large.
My another question: if we make a different module of the cell, like pouch cell and a button cell, something like that, how is the temperature stability of those kind of cells? Will it vary from pouch cell to button cells?
I don't think so. It would vary. The basic chemistry wouldn't change. But my worry about temperature here is probably it may speed up the kinetics. At the same time, it may also improve the dissolution. Yeah. So we need to look at this temperature effect on the capacity of these batteries with cycles. That's something we have to do. Right now, what I have shown to you, to all of you, is at room temperature. Okay, we didn't maintain any particular temperature. It was left at room temperature, so it was cycle. Yeah, but we do see some promising results. Probably as the center goes along, it will do also those kind of tests which any other battery company do before claiming it is commercially viable, right?
Yeah. Okay, there was another question from a student, but I don't know how relevant to you. But is the background in theoretical physics helpful for your research?
Oh yeah, I also see the question. There are two parts. I think the same Prevention Swine has asked, right?
Yes.
Yes. So I do see, yeah, see our industrial collaborators, they also work on this theoretical physics or like DFT type of theory they use to find out the good match between the separator that we use to the lithium polysulfide, right? So we need to use separators such that they absorb. Sometimes it should be act like a catalytic surface to put back this absorbed lithium polysulfates into action again. Otherwise, it will be like electrically isolated. It will be sitting on the separator forever, right? So all these can be tried, even by theoretically as well. Yeah. So finding a good separator, finding a good, ceramic layer or a host for your sulfur cathode. Yeah. So all that is possible. I feel this part of physics, theoretical physics, is very relevant for this battery research. Yes. So, and next question is, what courses are required to enter the research? I think you should just enter into the research institution.
Yes.
And then discuss with your guide. Definitely will tell you what are the courses that you should undergo if you are interested in theoretical physics related to batteries, or if you are interested in doing experiment as well as theory. Yeah. So almost in every institution, IITs in India has electrochemistry as one of the area of research, and I think the battery is very prevalent everywhere. It is omnipresent now. Any part of the world you go, almost all the institutions are doing this kind of research. Yeah, definitely you would find. Yeah.
Scope for that, right?
Yeah. Yeah.
Yes. I guess those are some relevant questions for that. So I lay this dash over the host.
Yeah. I think you are muted, Rudra.
I'm sorry. Yeah, I'm sorry, Professor. Thank you. Thank you, Professor Subramaniam. Indeed, to say it was really a very good session, and even I've enjoyed that, and I really didn't had any this thought about these project. Thank you once again, Professor Godindaraman and Professor Venkata Krishnan. Thank you, audience. Please stay connected so you can register for the next webinar. Thank you.